The last time we looked at the Pythagoreans introducing greatest common measure, and we looked at, yes, you could come in. Yes, it's important to save every second. So Pythagoreans started this greatest common measure algorithm, and we looked at implementation of the subtractive greatest common measure, and it was your homework. I begged you to do it, to try to come with a faster way of doing it. Of course, Greeks themselves knew the faster way, and let us see how they did it. Of course, I'm going to use somewhat different notation. It's not in Greek, but that's what we had. So this is a rewrite of the code which we had, which will help us to derive a faster version. Remember, we had while true loop and then trichotomy-based code, where we would, if things are equal, we would return. If one is greater than the other, we will subtract the smaller from the greater. And we keep going and going and going. Right? So here there is a simple change, and it appears to be slightly incongruous. What we do is we sort of check for b less than a for as long as we can. Right? Sort of the idea being that okay, pardon me. Sort of here we don't, and here we do. Sort of what we could do is that we could say, let us subtract b from a for as long as we can. Otherwise, let's swap them. Again, check whether they're equal. Again, somebody could object. We don't need to swap if they're already equal, but that will require me to put a test in between, and it's too early for us to optimize this code. So let us just look at this structure because it's important for us. Sort of while they're not equal, let us reduce a by b. So what do we get? If we think about it, this particular thing will get us a remainder. That is, it will get us a little chunk of b which is smaller than a when we are done. It's not quite true, but it's true enough to serve us. So there are a couple of interesting points. One point which deserves much longer treatment that I'm going to give it is so this is our remainder code. We're just factoring it out. Is this? Why does it terminate? Why our remainder code will terminate? It seems to be an obvious thing. Of course it should terminate. Well, it's actually not as obvious as you think. For example, let me give you a simple example of a definition of a segment where it will not terminate. If we define a segment to be either segment between a and b or a half line starting from a and going forever. Sort of, if we include point at infinity in some sense into our definition of a segment, obviously it's not going to terminate. It will go on forever. So interestingly enough, it took many, many centuries to sort it out. We need a special axiom. Actually, the realization that we need a special axiom for things like that goes back to the Greeks, as many, many other wonderful things, goes back to Archimedes. So what we need the following axiom. We need to say that for any two line segments A and B, the exist in integer n, natural number n, such that if you take enough b's, n b's, it will be greater than a. In other words, there are no infinite quantities. So if this is known as Archimedes' axiom, that is, that a finitely many b's could always exceed a. Right? It's an aside. Again, it's very, very important for example, sort of things like integration. When you separate, it's central to our understanding of the world, but I just mention it briefly because we need to go and look at our new version of greatest common measure. So if we have segment remainder, we could factor it out, and our segment GCM becomes very, very simple. We say, while they're not equal, do remainder and swap, do remainder and swap, do remainder and swap, and eventually they'll be equal. Right? If it terminates, that is, if they are measurable with the same measure. So in order to speed things up, what we need to do is to find a faster way of doing segment remainder. And the faster way was known not just to the Greeks, but to the Egyptians. Do you remember the scribe Ahmes, who wrote Rhind Papyrus in the first lecture? Or was it? Yeah, in the first lecture. Long time ago, in any case. So in the same papyrus where he came up with the fast multiplication algorithm, Russian peasant algorithm, remember the one which we studied? He also came up with fast division, division with remainder algorithm. And that's what we're going, I'm sure you all discovered it, but if you didn't do the homework, let's see how he did it. First, we start with some very simple mathematics. Of course, Ahmed just described the algorithm. He didn't quite do the mathematics, and his algorithm was somewhat different. So here, while the core of the algorithm which I'm going to present is fundamentally goes back to the Egyptians, the form which I give is fairly modern and wouldn't be quite understood by Egyptians. To compute segment remainder, we actually do an interesting thing. Typically, when we want to do a recursive definition of something, we say, let's go from n to n minus 1, right? Here we're going to do something utterly bizarre. We say, let's go from n to 2n. Let us assume that somehow we want to compute a remainder of a by b. Right? So what we're going to say, well, we don't know how to do that. Let's try to compute a remainder of a divided by 2b. So it's a bizarre upward recursion. And in order to do that, we rely on the following marvelous property, that a remainder dividing of a by b could be determined if we know the remainder from dividing by 2b with a very simple rule. If the remainder is less or equal than b, our Greek remainder doesn't go from 0 to n minus 1. Greek remainder works from 1 to n. Why? Because they didn't have 0. They had to shift the remainder. So first, we will do it their way, then we will go through many, many centuries and do it differently. So first we start with the sort of the Greek way. So we say that the segment is equal to r if it's less than b. Otherwise, it's just equal to r minus b. Okay, let us do something simple. You want to remainder by dividing by 10. Say, well, let's divide by 20. Somehow it's easier. We divide by 20, get a remainder. If the remainder is less than 10, we're done. If it's between 11 and 20, well, we'll just take away 10 and we'll get a remainder dividing by 10. Very, very simple idea, yes? Which leads to some utterly unbelievable code. Why it's unbelievable? Because it's not clear where the work is done. Let's just read the code. So we say that if A is less than B, we return A. Okay. Then we say if A minus B, we take it once, is less than B, and we can do it, by the way. Observe that we have very good guards here. We know now that A is greater than B after the first line. Right? Therefore, it's perfectly fine to do A minus B. We're guarded. So we do A minus B, and we say if A minus B is less or equal than B, we're sort of done. We already have a remainder. So we just return this A minus B. And yes, it would be nice to use a temp or something, but again, let us not concentrate on that. Otherwise, what do? We do this absolutely unbelievable step. We do upward recursion. We say, let us do fast segment remainder of A and B plus B with double B. And somehow, by hook or by crook, it will compute it. We don't know why, but we rely on that. And again, after we return, we just use the lemma, which we just proved, and say that if A is less or equal than B, then we return A. Otherwise, we subtract. So where is the work done? Who knows? I mean, you see what I mean? It's not, it's not clear where the work is done, but it works, truly. So why is it a parallel thing to Russian peasant algorithm? Because you see, we do this doubling. We say, let's keep doubling B till we cannot double anymore. And we keep doing it sort of till we're done. It's actually perfectly wonderful, except, of course, it's recursive. We have to maintain the stack. So the interesting issue which we need to solve is whether we could do it iteratively. We will solve it in a few minutes. But I'm just saying that in general, this is something which you need to sit at home and contemplate. It's a Zen-like experience, looking at this code and wonder, when I wrote it a while back, I couldn't believe that it actually would work. It couldn't possibly work. It worked mathematically, but of course it couldn't possibly compute anything. And when it did, I was very impressed. So, so now we could obtain fast version of segment GCM, which is not going to go slowly one by one subtracting, but going to do doubling till we're done, and we're going to be much, much better. Again, remember, if we're not commensurable, I mean two segments, nothing will help. So whether you go slow or fast doesn't make much of a difference. When you're going forever, you're going forever. So very nice code. So to do the next thing, to do any progress from that point on, we have to discover zero. And I have to tell you a little bit about discovery of zero, because there are all kinds of rumors who discovered zero, whether Indians discovered zero, whether Arabs discovered zero. Well, as a matter of fact, zero has been around for longer than either Indian mathematicians or Arab mathematicians. Not that Indians didn't make a fundamental contribution. You will see how they made a contribution. As a matter of fact, Babylonian astronomers, long time ago, in their calculations, used zero profusely, except they were doing calculations as base 60. So there was this totally unwieldy base, but there was a zero. By the way, Babylonian merchants at the same time. And Babylonia was a huge empire with lots of trade and things like that. So they needed to do their accounts. They, of course, were not using base 60. It's not good for accounting. They were using base 10 without 0 for many, many, many centuries. Eventually, Greek astronomers inherited Babylonian computations and merrily continued to use base 60. Again, for centuries. They did introduce 0, and by the way, they wrote 0 as in Omicron, a Greek letter, little o, you know. It's remarkable how things stick around. But again, never ever they tried to use decimal notation. This was specialized sort of notation for astronomy because that's how you measure positions in the star. I mean, it got stuck, never broke to the rest of the mathematics. So the idea was there that, moreover, the sad fact was practice was there because at least since about 6th century BC, every merchant in the ancient world had a computer. You didn't know that? That's how they looked. At least when I was young, that's how these computers looked. This is called an abacus. And there were different shapes. Some of them had rods, some of them had stones and grooves, but spread around like a wildfire. Was in Rome, was in China, was in Babylon. Nobody knows who invented it, honestly speaking. This is actually a Russian abacus. And I'm sure that, like Boris, still remembers. Because when we were young, there were no calculators. Not even in the United States. We're that old. We're pre-calculator age. And important banks and other places in Russia, they used mechanical arithmometers. You go crank, 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 and something comes. But stores didn't use arithmometers. So people who were doing, inventories, whatever, store accounting, used this device. And they could compute things very, very fast. I don't know whether Boris remembers. They would go to sort of...
Not necessarily correct.
Not because they couldn't. Well, moreover, it was correct from their point of view.
For that, so they use both hands to do the same calculation simultaneously.
They knew what the result should be. So it's right. So in any case, and obviously, if you have an abacus, there is an implicit 0. And there is a decimal. You see there are 10 things. So it was widely used. However, there was no decimal notation with 0 any place. Till very, very late. Because, yes?
Just a question. Were there base 10? The abacus is like...
Yes. Yes. The question I have to repeat. Whether abacus was base 10. Yes. We have absolutely no evidence of base 60 abaci or 6. I mean, again, of course, there were, tribes which used a fuzzy binary system, 1, many. But then you don't need abacus. So for literally thousands of years since the invention of abacus, probably till the 6th century AD, nobody tries. Again, Indians eventually do, but even Aryabhata, who is the greatest Indian mathematician, doesn't have 0. He does have 1, 2, 3, 4, 5, 6, 7. I mean the Indian numerals, but not 0. We do not know. I mean, who introduced 0. So it starts spreading some time around. We're fuzzy. It's hard to tell. Sort of, and goes from India to Arabs and then spreads through the Arab world, which at that time gets to be really huge, from Samarkand to Toledo, from Spain to Central Asia, enormous world, and they sort of start using 0. So apparently by 9th century, it's all, yes?
Did anybody use positional written notation without the 0?
Yes. It would be positional system, but they would have special 10, 100. It would be positional. Think about it. In some sense, Roman numerals are sort of positional. You sort of keep shifting, but you introduce a new kind of digits for tens, for hundreds.
Yeah, but you could just have 10 digits.
No, but they didn't have 10 digits. That's the peculiar thing, that astronomers had 60 digits, but merchants didn't have a sign for 0. Nobody had sort of, they would write sort of the least digit. For example, you would write 11, you would write 1 and 10. It's positional, if you like. Exactly right. Because you cannot repeat 1. You couldn't shift 1. It gets all sort of confusing. So it's the introduction of the 10th digit for the base 10, which was the breakthrough, which happens again clearly in India. We do not know exactly when, and we do not know who.
And it's also very obvious in Chinese number system. You should always read the exact number up without 0. Like 11 means what you read is 10 1. 111 is 110 1.
Yes. So yes, because it's again, it took a while. It's not clear why, guys. But sort of we have to understand that certain things we as a species are very, very conservative. Sort of the fundamental how we count is very basic. If you don't have a notion of 0, it's very difficult, even if you are sort of a scholar, to introduce it, because you have to affect everyone in the society, right? Sort of, it has to. I mean, it's. For example, let us see how it happens in Europe, because about that we know it very, very well. Sort of there, the history becomes much, much clearer. But again, it takes enormous time to get to Europe. So by 9th century, Arabs use 0 profusely. There is no indication of anybody in Europe using 0 till the year 1201, the beginning of 13th century. So we're talking about 300-400 years before it gets to Europe. And don't forget, I mean, Arabs themselves, I mean Christian Europe, Arabs themselves are in Spain. Most of the Spain is Arab. They use 0, but somehow it does not cross the Pyrenees. And it never did cross the Pyrenees. We did not get it through that route. The route was very, very different and very, very interesting. Here we have to go to the next sort of major point, sort of what happens in Europe, Western Europe. But even Byzantium, which maintains very, very high culture, but the mathematical studies decline. Gradually, year after year, they decline. They still copy Euclid. This is why we have Euclid, because they sort of faithfully copy him. But sort of gradually, say by the 6th, 7th century, very few people work past the end of first book of Euclid. What is at the end of the first book of Euclid? Anybody knows? Pythagorean theorem, proposition 47. Yes, so people work the first book, but the rest is copied, preserved, maybe studied occasionally by someone. Actually, I have no indication that anybody in Byzantium sort of really reads the stuff. They copy, they know it's very important, but sort of past the first book drops out of curriculum. It's for advanced studies, which nobody seems to do. And in the Western Europe, things decline dramatically. Sort of the only thing which is preserved is Euclid without proofs, translated into Latin by Boetius, probably. So, you know, the knowledge sort of declines. And there are multiple reasons, very different between Byzantium and Western Europe. Western Europe, I mean, the main reason for decline is the total destruction of the Western society by the Normans. I mean, first, all kind of Germanic tribes, and then Huns, and then Normans come and just whatever is left, they wipe out. So by, say, the 10th century, things look utterly hopeless. Sort of the reconstruction of Western civilization does not appear to be possible, sort of when you look at the state. It is, and the high civilization is Arabs. If you want to learn, you have to go to Baghdad or Cairo or Cordoba, or you know, you have to go to the Arabs because they preserve civilization, not just books. There are a few books in the West, but civilization is almost gone, 10th century. Then sort of things change. And in the 11th century, things start looking better. There is a sort of something happens. It's very clear that something changes when we look at the architecture. And especially when we go to a certain part of Europe called Italy, things start looking good. Even as early as 11th century, things change. And let's go to a great sort of place in Europe in the year 1200. Anybody knows what it is? Pisa. Yes. That's where we're going to go. This is this glorious, all of you have, of course, heard of the Leaning Tower. It's a minor thing. Campanella is wonderful, but nothing compared with Il Duomo, the great cathedral. If you stand there, you're overwhelmed. And there's this baptistry here. It's not in the picture. There is this gorgeous square which Gabriele D'Annunzio, 20th century Italian poet, called Piazza dei Miracoli, the miraculous square. And it is indeed one of the most miraculous things, especially during the full moon. If you really want to see something special, go to Pisa and stand there during the full moon, and don't look at the souvenir stands behind. So, sadly enough, that's a sign of modernity. You could buy all of that in plastic made in China, right there, for €3. So, don't. So this was the center of the world. Why? Because believe it or not, Pisa, which is right now, is totally inland community, was at that time a great naval power. They had the greatest navy in the Mediterranean, or at least they aspired to be the greatest navy. Of course, you know, there were all these Arab navies quite strong, but they would fight them. They would fight Byzantines. They established a great naval trading republic. It's not Venice, as you would think. It's not Genoa. It's Pisa, which appears to be the dominant power. This is why they could build such a cathedral. You need funds, and they have funds. They're doing very, very well. They trade with Constantinople. It's, say, somewhere around 1100. There are probably about 1,000 Pisan traders in Constantinople. They have a major trade representatives, and they have trade representatives all throughout Mediterranean. So people travel. You say, so what does it have to do with mathematics? Yes, it has to do everything to do with mathematics, because this is the guy who was born in Pisa, and his father was a trade representative of peace and republic in Tunisia among the Arabs. Leonard de Pisana. This is the name you should hear everywhere, but of course you don't. You have heard of him under his pseudonym, which he never heard of, but he is known now as Fibonacci, son of Bonacci, and he is known because of some funny numbers. They're important numbers, but his contribution exceeds these funny numbers by a factor of gazillion. So he's one of the most crucial people in the history of Europe. He changes sort of Europe from not being a mathematical power to suddenly becoming first-class leading mathematical power. One guy, right? Changes, sort of brings mathematics back to Europe. So what does he do? Sort of, as a kid, his father tells him, come to Tunisia. And he does. And as he writes in the introduction to one of his great books, we'll talk in a second, so he goes there, learns Indian numerals. And then he becomes a trader, probably, we don't know. But again, he writes that he visits lots of places. Again, Egypt, Syria, Greece, Byzantium. Sicily. Sicily is a very major, we'll see in a second, very major cultural and sort of political center at the time. Provence, sort of he travels all over and keeps assembling mathematical facts. Again, this idea of going some places and learning is obviously comes back to Europe. Sort of, he is willing to go to Arabs to learn, right? Not to fight. He's not a crusader. He's a learner. He's a student. And he learns enormous amount, obviously, because by the time he gets back, he's about 30. In 1201, he writes this great book called Liber Abaci, which is the book of abacus. Mind it, it's not a book of abacus. It's a book of how to go around without abacus. But it's effectively, it is the first book of computer science. Because freedom from abacus, sort of how to do it on paper without using the stuff. And what does he do? You actually studied all of his algorithms for many years. Do you remember when you went to elementary school? You studied long addition. Did you study long addition? All of you. Long subtraction, long multiplication, long division. Who described the algorithms for the first time, at least in Europe, in a systematic way? He did. So this is, I mean, again, these are not like emerged out of nowhere. There was a guy who wrote them down, and gradually over centuries they spread. Again, it was a revolutionary thing. Right? The book, by the way, is still today an amazingly, I mean, he was not just a repeater of what he learned among the Arabs. He was clearly the greatest mathematician of his time everywhere, anywhere, and of great depth. So he became quite famous in Europe, so famous that the greatest political leader of Europe at that time, emperor, the Holy Roman, you know about Holy Roman Empire, there is this sort of the greatest political concoction of Middle Ages, and the head of it was Friedrich II. He was known as Stupor Mundi, the wonder of the world. And not just because of his great military skills, which he did have. He was probably the most educated person in Europe at that time. You know, do we have political leaders who are the most educated people of that time? No. But at that time it happened, he knew Italian, living in Sicily, German, being, you know, emperor of Holy Roman Empire, which covered most of Germany. Trivial. Latin. Well, many people knew Latin. Greek. Nobody knew Greek. Okay? He is even 70 years after, Thomas Aquinas didn't know any Greek, maybe 3 words. Right? Great mind he was, but didn't know any Greek. Arabic. How many people in Europe knew Arabic and could write it? He could. He had Arab scholars at his court in Palermo. Right? And some people say it's doubtful, even Hebrew. And nobody knew Hebrew at that time. Again, yes, I mean, some Jewish Talmudic scholars did, but it wasn't absolutely not known among non-Jews. So apparently he was this unbelievable scholar, was interested in all kinds of sciences, brought scholars from all over the world to his court. The greatest scientist was Michael of Scots from Scotland, but also from Arab world, from everywhere. It was a very cosmopolitan court, traveled everywhere, and at some point he gets so excited about Leonardo di Pisano's accomplishments that he decided to take his court and maybe to Pisa, maybe they meet some other place, but they go to a special place, and there is a great competition, a tournament, where Leonardo sort of faces all the court mathematicians and defeats them. He could solve all their problems, they cannot solve his problems. So he's clearly the greatest man in the world, and grateful Republic of Pisa pensions him off. So that's my dream. So, but he's clearly sort of was a great towering figure. Unfortunately, after his death, his work, while spreads much, much slower than we would want. But Italy becomes the center, and one of the sad parts of this course that I cannot put a discussion of Italian Renaissance in. It doesn't quite fit in my 4 journeys. And let me just tell you, it's a remarkable period. I wish I could, but you know, my boss Dan here does not allow me to introduce gratuitous stories into the course. They have to be related. I'm sure you see how they're always related. So, so this is our only visit to Italy. But for several centuries, the center of mathematics is going to be in Italy, and this idea of Italians building up, of course, on work of Leonardo di Pisano, but also borrowing from Arabs, is going to be quite central to the history of mathematics. And you need to know just the names of people like Tartaglia and Cardano, people who introduced Europe to algebra and who made algebra, obviously an Arab thing, a European science. We'll talk a little bit more about that during the 3rd journey, the gifts of the Arabs. So what did he write? The first book I mentioned, and he did a couple of editions of it. There is a wonderful English translation available. Those of you who are interested could stop by at my office. By the way, talking about stopping at my office, my friend Paul McJones donated another bunch of elements of programming. And those of you who do not have a copy, please stop by and get it. It might help you, at least during the treatment of the material from the 2nd journey is clearly there. But whatever. So he writes a bunch of books. The most significant from my point of view is other than the most significant is Liber Abaci, but Liber Quadratorum, the book of squares, is the greatest number theory text between Diophantus, the Greek, and Fermat. Remember? Pierre de Fermat, the Frenchman. So this is the greatest book, and you're going to get some homework from this book. So some homework problems. The first problem, which is very easy But you have to do it. I'm not going to do it here. But we need to spend just a couple of minutes thinking about it. Why was it a difficult problem? Why the Greek mathematics had such a difficulty discussing these things? Because you see, for the Greeks, that read like that. Start a non-terminating algorithm here, wait for the result, get to start non-terminating algorithm there, wait for the result, and when both non-terminating algorithms terminate, you add them together, and it will be equal to the result of the third non-terminating algorithm. They were just, for them, that sounded like utter nonsense. Remember, they could do square roots. They moved mathematics from arithmetic to geometry in order to have square roots. Because, with ruler and compass, you could, with finite number of steps, compute any quadratic square root containing quantity. A plus b square root plus square root of c plus d, whatever. They could do that. So they terminating computation with ruler and compass. But cube roots couldn't do. There's just no way to do them. And now we know that they were right. There is no way of doing it. So it was somewhat difficult issue. And what the step which sort of Leonardo does, remarkable step, he says, I don't really need to think about whether it terminates or not. I'll just designate this quantity. And to solve this thing, you need the quantity called cubic root of 2. I'm giving you a hint. So he says, I don't know what it is, but I'll just designate it as if it exists. And then do the rest of the proof. So something which a Greek mathematician would feel utterly uncomfortable because it's just wrong. And it is wrong. But that's the first step. We'll see it's a very, very powerful step which allows enormous progress. So this is work on this problem. This is a problem of medium difficulty and related to the material which we covered. And the third problem, which he solves in Liber Quadratorum, is hard again. Anybody in this room who really tries could do it, but it's not going to be easy. But it's of great importance for later development of mathematics. Like Fermat builds on it. It's one of the steps to the modern number theory. Maybe could we have a break now a little bit earlier?